This aircraft model is in a high-speed wind tunnel. As was shown in Part 1, we can make visible changes in air density around the model as the tunnel airspeed is increased. Regions where the air is being slowed down, becoming denser, appear red. Regions where it's speeding up and becoming less dense appear blue. Now, let's start again. This time we'll take the model right through the transonic speed range where conditions are particularly unstable. To understand what is meant by the transonic range, we must first examine what happens to the airflow around an aerofoil at a small angle of incidence. Soon after the critical Mach number, a shock wave forms on the upper surface. Let's stop the picture a moment. Here is the supersonic region, shown in a lighter green. The flow everywhere else is subsonic. As the airspeed is increased, a lower shock appears. Both shocks start to move back. Then the upper one stops because the boundary layer breaks away from the surface with a lot of turbulence. This is called flow separation. When the lower shock has reached the trailing edge, the upper one moves back. Near Mach 1, both shocks meet at the trailing edge. The flow separation is now much less. As before, light green is used to show the supersonic regions. The flight Mach number has just passed Mach 1. The free air stream is supersonic now, and another shock wave appears in front of the wing, the bow wave. It's something like a bow wave on the surface of water. As before, the supersonic regions are lighter green. Like the shock waves on the wing, the bow wave is formed by the constant piling up of pressure waves, this time from points near the leading edge inside the subsonic region. As speed increases, the bow wave comes in quickly towards the leading edge, but there's still a subsonic region in between. A shock wave oblique to the airflow usually has supersonic flow on both sides of it. A normal shock, one perpendicular to the airflow, always has subsonic flow behind it. As the speed continues to increase, the shocks bend back still further. At a high enough Mach number, provided the leading edge is sharp, the bow wave attaches to it. Again, here's an attached bow wave on water. The flow everywhere is now supersonic. So when considering airflow, it's convenient to divide flying speeds into three ranges. The subsonic speed range, covering all speeds at which the flow everywhere around the aircraft is subsonic. The transonic range, covering all speeds at which the airflow is mixed, part subsonic, part supersonic. That is, from mcrit to about Mach 1.3. And the supersonic range, covering speeds at which the main flow everywhere is supersonic. Those bangs were shock waves from an aircraft in transonic flight. Let's see one of the ways in which they can be formed. As soon as the aircraft passes Mach 1, a bow wave appears. The aircraft pulls out of its dive and slows down below Mach 1, but the bow and tail waves travel on. They strike the ground, where they are heard as... The same sort of thing may happen with an aircraft flying at a steady speed above Mach 1, either transonic or, as here, supersonic. To reach the supersonic speed range, all aircraft must pass through the transonic range, where shockwave troubles are at their worst. Slight changes in speed or in attitude make the shocks move violently. But it is flow separation that causes most of the troubles in the earlier part of the transonic range, when separation. Once the shocks have reached the trailing edge, separation is much less. It is flow separation that causes the shock stall, so called because the effects in flight are rather like the normal low speed or high incidence stall, also caused by separation. The first shock stall trouble is a sharp rise in drag. At speeds below M crit, drag is roughly proportional to the square of the speed. But when shock waves develop, they cause a much greater rise in drag. For the energy dissipated as heat by the shock wave must be continuously supplied by the engines. This causes a new kind of drag, wave drag. As the shocks move back and grow stronger, so the wave drag grows. So once an aircraft has passed its M crit, its drag rises much more steeply than before. Above Mach 1, the wing shocks have reached the trailing edge and now grow much more slowly. The wave drag of the bow wave also changes, but gradually. So the drag rise becomes less steep again towards the upper end of the transonic range. These changes in drag can be seen more clearly in the behavior of the drag coefficient. At low Mach numbers, the drag coefficient at a constant angle of incidence doesn't change. But above M crit, this happens. This is the transonic range, and the sound barrier is simply the peak in the drag coefficient somewhere around Mach 1. So much for drag. What happens to lift of the shock stall? It drops suddenly. Again, watch the behavior of the lift coefficient. Like the drag coefficient, it's constant at low speeds. Somewhere below M crit, it starts to increase slightly. This is because the air is becoming less dense as it speeds up over the curvature of the wing. But just above M crit, flow separation makes it plunge suddenly downwards. Later on, it increases slightly, then falls again. The shock stall can also cause instability. For instance, changes in fore and aft trim. First, lift increases slightly just below the shock stall. This causes the aircraft to gain height. That is, assuming the pilot takes no correcting action. Next, at the shock stall, the sudden loss of lift puts it nose down. As the Mach number increases, the bottom shock appears and reaches the trailing edge before the top one. This forces the nose up a little. Finally, the top shock also moves to the trailing edge, making the aircraft go more nose down again. Most aircraft don't do all of these things, but the center of lift always shifts towards the rear when passing through the transonic range. So all aircraft suffer a final nose-down trim change. Other kinds of instability can be caused by flow separation. Wing dropping, porpoising, snaking, and Dutch roll. Movements something like these. There is also buffeting, caused by the turbulent separated airflow from the wing striking the tailplane. Or separation may affect other parts of the aircraft directly, such as the wing root junction or the cockpit canopy. Finally, the controls may lose their effectiveness. There are two main reasons for this. At subsonic speeds, a control surface affects the air all round the main surface, as the smoke streamlines show. For instance, moving an aileron affects the pressure distribution round the whole wing. But when a shock wave is present, the aileron has a much smaller effect. For any changes behind the shock wave can't affect the air ahead. Secondly, the control surface is not fully effective even behind the shock wave, for it's moving about inside a region of separated airflow, which, although turbulent, is aerodynamically dead and can't exert much force on the aircraft. But this turbulent wake can cause violent oscillations of the control surface itself. They are accompanied by large fore and aft movements of the wing shock waves. In this picture, the movements have been slowed down 40 times. These are the chief troubles which the pilot may meet when he comes up against the shock stall. Changes in incidence during maneuvering, for example, modify the whole shock pattern. And by doing so, they bring on the shock stall below the normal critical Mach number. Compare these two identical aerofoils of the same Mach number, but with different angles of attack. How can these troubles be met? In part one, we saw that two design features, thin wings and sweepback, raise the critical Mach number and postpone the shock stall to higher speeds. But exactly the same features, thinness and sweepback, lessen the effect of the shock stall itself. Flow separation can also be made less severe by fitting vortex generators, rows of small metal vanes, each of which leaves a tiny vortex behind it. These vortices stir live, fast-moving air into the sluggish boundary layer. These two pictures are of the same aerofoil. In the upper one, vortex generators are fitted. They can be seen jutting out in silhouette. Separation is reduced in the upper picture, and the shock wave is further back. The extra shock wave produced by the vortex generators themselves is a weak one. This principle of reinvigorating the boundary layer may one day be applied by blowing air into it. Buffeting is reduced by putting the tailplane out of line with the wings, so that the turbulent airflow from the wings now misses the tail entirely. But the tailplane has its own system of shocks and separation. Trimming power and elevator control are still limited. A much greater effect can be obtained with the all-moving tailplane. Either the trimming tailplane with separate elevators, the all-moving tailplane with geared elevators, or a single moving surface called a slab tail. Such moving tailplanes can give up and down trim control with much smaller deflection than the elevators on fixed tailplanes. For proper control at transonic speeds, powered controls are almost essential to overcome the huge forces on the control surfaces. All these improvements in design are reducing shock stall troubles in the difficult earlier part of the transonic range. Still, faster flying is only possible when wave drag can be reduced. The drag caused by the shock waves changing kinetic energy into heat. A new design principle helps to do this. Area rule. Consider this aircraft. Take a section through it at right angles to its axis. So, represent the cross-section on a graph. Do this at points all along the axis. The resulting curve is irregular. Let us redesign the aircraft to smooth out the bumps in the curve so that the cross-section area changes gradually and not abruptly. So instead of the curve with bumps, a much smoother curve is obtained. This means the fuselage must have a waist to compensate for the wings and must flare out again behind. Above Mach 1, the bow wave adds its own drag. This can be reduced by having leading edges, nose, sharp rather than rounded. Compare the effect on the bow wave of sharp and rounded leading edges. In these ways, designers are gradually solving the problems of transonic flight and building aircraft that are safe at high and low speeds. Many aircraft have already mastered the shock stall and don't suffer from it at all. Others, which for many years to come will be flying transonically around Mach 1, are doing so with greatly reduced shock stall effects. Soon, still greater thrust will be available from afterburning jets, ramjets, and rocket motors. Aircraft whose job it is to fly as fast as possible will be able to pass easily through the transonic range into the steadier and more predictable range of fully supersonic flight.